All right, Unit 5, Lecture 2, we're doing a little bit more on implicit differentiation, and then we're going to get into calculus word problems. We'll call related rates problems. We're going to be taking derivatives with respect to a different variable. We'll talk about that more. But let's first talk about more implicit derivatives, and in particular, finding locations of horizontal or vertical tangents. We should remember horizontal tangents. We always think of lines that are horizontal having a slope of 0. So when you got dy dx, that's equal to 0. Okay? You got no rise. You can have whatever run you want. It doesn't matter. The slope is 0. Vertical tangent, a slope of a vertical line is undefined. What do I mean by undefined? I mean you have some rise, but you don't have any run. So when we take derivatives and we get dy dx, if we want to find a horizontal tangent, as long as my numerator equals 0, I'll be able to find when the entire dy dx is 0. So long as the numerator and denominator are 0, that's undefined. For vertical tangents, as long as my denominator equals 0, then, and my numerator is not 0, then I'll find a location of a vertical tangent. So that's what we're going to be doing. We're going to be finding horizontal and vertical tangent locations for implicit curves. Well, for all of these situations, to find these tangents, we will need the tangent slope generator. So you will need to find the derivative of this to work your way to find dy dx. So let's go ahead and take the derivative. Now, you guys should be doing this in class by yourselves and maybe just looking up to confirm that your answer and my answer are the same. I'm going to subtract the 8x. I'm going to add the 8. I probably should show the work. Minus 8x plus 8. I'm going to factor out the dy dx. And then I'm going to divide. Okay, cool. So, horizontal tangent. Dy dx equals 0. As long as my numerator equals 0, I'll find the horizontal tangents. X equals 1. Great. Vertical tangents. Dy dx is a number over 0. Denominator equals 0. As long as I find when my denominator equals 0, I'll find all the locations of my horizontal tangents. Boom! When x is 1 and y is negative 2. Now, this isn't a point. X is 1, comma, negative 2. You're not going to write this down. Okay? Because it, we don't know. Like, if the question asks us find the x or y coordinates of the horizontal or vertical tangents, we'd be like, done. I'd say, okay, horizontal tangents occur when x equals 1. Vertical tangents occur when y equals negative 2. But they want, and this is part of reading the directions, the xy coordinates of the horizontal and vertical tangents. So I need to find the y locations when x is 1. I'll need to find the x locations when y is negative 2. So let's go ahead and find these xy's. Let's start with when x is 1. When x is 1, I get 4 plus y squared minus 8 plus 4y plus 4 equals 0. Well, that's y squared plus 4y. I got 4 minus 8 plus 4. Okay, well, that's 0. That's just y squared plus 4y equals 0. I can factor and solve. Oh, that's interesting. I get 2 y's. So that means my horizontal tangent, there's actually 2 points. There is 1, 0 and 1, negative 4. Vertical tangents when y equals negative 2. Let's plug in negative 2 for y. I get 4x squared plus 4 minus 8x plus, this will be negative 8 plus 4 equals 0. Let's see. I get 4x squared minus 8x. The 4 minus 8 plus 4, that's 0, so that's nice. I can factor out the 4x. I get x equals 0 and 2. So I have two vertical tangents. Vertical tangents occurring when y is negative 2. My vertical tangents will be at x is 0, y is negative 2. X is 2, y is negative 2. Now let's just confirm. I'm going to go ahead and graph this so that we can confirm that we are correct. We got 4x squared plus y squared minus 8x plus 4y plus 4 equals 0. And I got this oval, okay, or an ellipse. I see a horizontal tangent at 1, 0 and 1, negative 4, just like I said, 1, 0, 1, negative 4. I see a vertical tangent at 2, negative 2 and 0, negative 2. 2, negative 2, 0, negative 2. So there you go. Look at what we just did. Pretty cool. All right, let's go ahead and you guys do this. I'll do it as well. And you should be checking your answers with me and my work. Let's do that for this situation. Find the horizontal and vertical tangents. So let's go ahead and just find the vertical tangent locations. Because when I find the x, what we'll find is that it's going to be tough to find the y. So, why don't we just stick to this? Find the x or y locations rather than the point locations. That sometimes makes things easier. In this situation, I wouldn't want you to have to plug in these y's and do a lot of arithmetic and find x. You could, or plug in x and try to find y's. You would not be able to. So instead, horizontal tangents, when your numerator equals 0, that's when x equals 0. That's fantastic. Vertical tangents, and we'll just leave it like that. When my x coordinate is 0, my vertical tangents, y squared plus 4y minus 5 equals 0. That's y plus 5, y minus 1. So that's when y is going to be equal to negative 5 and 1. And just with those, that's pretty powerful information to know. If you graphed 1/3 y cubed plus 2y squared minus 5y minus x squared equals negative 4. It's a cool looking graph from what I remember. Ends up looking like the thing in the back of your throat. And you can see a horizontal tangent at x equals 0. We'd be able to find that y coordinate. Vertical tangents here when y is 1 and when y is negative 5. Okay, so there's my vertical tangent here, there's my vertical tangent here. Okay, more. Let's just do horizontal tangents here. Or might as well do vertical, because we're not used to finding vertical tangents. Let's look at this one. X squared plus xy plus y squared equals 27. So let's go ahead and take the derivative. Why is this tougher? Derivative first, okay, derivative of x squared, derivative of x times y plus derivative of y times x. Derivative of y squared, derivative of 27. Subtract the 2x, subtract the y, factor out the dy dx. from the remaining terms, divide to solve. Okay, here's why it's tougher. For my vertical tangents, when my denominator equals 0, I have an equation. I have two variables, x plus 2y. Unlike the previous two examples, I'm not easily able to find x or y. I was easily able to find x and y in the previous examples. Instead, I just have x plus 2y. Like, what do I do here? Well, here's the key to this. We have a system. This is an equation. Our points must satisfy this equation to be a vertical tangent. And this is an equation that all my points must satisfy to be on the curve. So I have two equations and two unknowns. I will substitute to solve my system, just like we substituted before. What is going to be easiest to do is to solve this for a variable. Once I've solved it for a variable, I'm going to plug it back into that original equation. Let's go ahead and do that over here and see what happens. When I have x, I'm going to replace it with negative 2y. So in parentheses, I got negative 2y squared plus negative 2y times y plus y squared equals 27. Let's see what happens. Simplify. I got 4y squared minus 2y squared plus y squared equals 27. This is 2y squared. That's 3y squared equals 27. Divide by 3, I get y squared equals 9. Square root y is equal to plus or minus 3. Now let's go back to asking you, find the x comma y, so the point locations. So most people think, oh, okay, I know what y is. To find x, plug it back in to my original equation. But remember, with systems, you could plug into any equation in our system. The easiest equation to plug into would actually be this original one, even that one. Plug into your derivative equation. To find x. So when y is 3, x is negative 2 times 3, so that's negative 6. So I have the point negative 6, 3. And when y is negative 3, x is negative 2 times negative 3, which is positive 6. So I have the point 6, negative 3. Okay, so these are my answers. And notice how this is a little bit more involved, something like this. You have a system, you need to substitute back in. So be ready for that. I'll show you how we succeeded. X squared plus xy plus y squared equals 27. 6, negative 3, 6, negative 3, vertical tangent. Negative 6, 3, vertical tangent. We'd be able to find the horizontal tangents the same way. Okay? All right, so that's a tougher horizontal vertical tangent problem. You'll see some like that on your homework. But let's move on. We also know about the uses of a second derivative. Second derivative tells us whether something's concave up or concave down. And we are going to want to do that with these curves. Now, typically, you'll be asked to find, let me give you a different equation instead of 25. Let's go to like 26, and let me give you the 0.51. Typically, you're asked to find a second derivative at a point. Let's see how we're going to do that. But I'm going to show you how sometimes you won't be. But let's find the second derivative at this point. Here we go. Just like we are used to, we are going to want to take the derivative twice. But the problem is, I don't want to take the derivative in this step. I usually like to take the derivative of dy dx. So I need to solve for dy dx. I'll subtract the 2x divided by 2y. I'll get negative x over y, right? Because the 2's will cancel when I divide. So then we'll take the derivative again. So here we go. Let's take the derivative again. I would get d squared y over dx squared. We are comfortable with that. I have to use the quotient rule. Let's remember the quotient rule. Derivative of the top times the bottom minus the derivative of the bottom, the derivative of y is dy dx times the top all over the bottom squared. Okay. Here's an issue that we are not familiar with or seen before. dy dx. We have a second derivative that includes my first derivative. What are we going to do with that? Well, it's actually not as complicated as you think. You know what dy dx is equal to. If you wanted to, you could plug in negative x over y. However, you just want to try to find what it is at 5,1. So if I want to find this at 5,1, I would just start plugging in 5 and 1. But when I get to dy dx, this part, I'll just have negative x over y. Well, negative x over y, negative 5 over 1, negative 5. Here, the x turns into negative 5 as well. The y squared would be 1. So this is negative 1 minus 25, which is a slope of negative 26. That's not a slope, it's a second derivative. What does this tell me? Well, it's the rate of change of my first derivative, so it kind of tells me the acceleration, but we remember that the sign of the second derivative is the concavity. So x squared plus y squared equals 26. We would say is concave down at 5,1. Now I'll show you how we can actually go a little bit further and show concavity a different way. At the point 5,1, 5, 1, 5 is right there, 1 right there. Second derivative is negative. You can see my graph is concave down. That's the extent of what you'll do in the second derivative. I can actually show you how we can simplify this tremendously, but it's never something that you're going to be asked to do. You will be asked, though, you will be asked to write down the second derivative in terms of x and y. So you will be required for some questions to plug in what dy dx is equal to, and this would be your second derivative in terms of x and y. There's a lot of simplification you could do with this. A lot. But I'm not going to worry about it. You don't have to worry about it, because typically you're going to be asked to find the second derivative at a point. Don't worry about showing. Let's get rid of that. Just find the second derivative at, let me pick a point. When does the square equal the cubed? 1, 1. That's it, though. Sure. Let's go with that. See what happens. It might not work out well. So, derivative of 2y dy dx equals 3x squared. dy dx is 3x squared over 2y. you'll see on your homework that there will be questions where I will give you the first derivative. I'll do one like that next to this. And you will be asked to find the second derivative from your first derivative. So I'll show you something like that in a second. Derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. If you wanted to write this in terms of x and y, you would take what dy dx is equal to and plug it in. If I want to find this at 1, 1, I would get 6 times 2, which is 12, minus 2 over 2 times 3 times 3. So 12 minus 9 over 4. That's 3/4. All right, what's that? Cool. Now here's another example. So find space in your notes. If dy dx equals 3x times 2 minus y, find d squared y over dx squared at the point 2, 3, which is on the curve of the original function. Okay, this is something you'll see as well. You'll start with the first derivative. You'll take the second derivative. You will find that you will need, certain rules, not necessarily the quotient rule. The derivative of here, we'd have the derivative of 3x times 2 minus y will be a product. So derivative of the first times the second, plus the derivative of the second, that'd be negative dy dx times the first. You need to be prepared to write this in terms of x and y. So be prepared to replace dy dx with what it's equal to. And then plug in 2, 3. Okay, so I get negative 3 plus, this will be positive 6, which is 3. Okay. All right, so that's it for implicit derivatives, okay? We did horizontal and vertical tangents. We did second derivatives. You will see more questions on your homework that will prepare you. Let's now switch over. We are going to introduce calculus word problems in this lesson. We are going to get away from taking derivatives with respect to x, which we've been doing. Why? Because we've been focusing on tangent slopes. Change in y over change in x, right? Slope. And we were comfortable with using the chain rule, where I got 3y squared, but then I need the derivative of y with respect to x after that. And what you would find is actually, the derivative of x is 1, but watch how I could have just done the kind of chain rule idea of things. I get dx over dx, that's 1. We are now going to shift gears to see how quantities change with relation to time. We are going to say, like, how quickly is y changing at a specific moment in time, rather than how quickly is y changing versus how quickly the x is changing, which is slope. Okay, but this is starting into, and we will lead this into our unit 7, our first unit after the break, which will be talking about physics and position, velocity, acceleration, that fun stuff that's in store for you. Before we get there, though, we're going to do these calculus word problems. And we are going to see how quantities change at a specific moment in time. So watch what happens. No longer is d the derivative of y dy dx. It is now dy dt. 3y cubed. No longer 3y squared dy dx. It's 3y squared dy dt. The derivative of x, no longer 1. Because of this dt, we are saying the change in x at a specific moment in time, dx dt. It is when we take the derivative of t that we will get 1 dt over dt. Okay? So, what we are used to saying as 2x plus 2y dy dx actually is more complicated. 2x dx dt is the derivative of x squared. 2y dy dt is the derivative of y squared. We'd have to use a chain rule for everything besides t. If I have x times y, derivative of the first is not 1, it's dx dt times the second, plus the derivative of the second, that's dy dt times the first. We will be taking derivatives of formula, like distance formulas, volumes. We will see, starting next class, but really starting today, what we can do with these equations and how we can find how quickly things are changing. Lots of dy, dt, dx, dt, dz, dt, but that's what it is. Take the derivative with respect to t of v equals 4/3 pi r cubed. Yikes. Let's see. Maybe this is tough. It's actually not that tough. I'd have dv dt equals 4/3 pi, just a constant. Leave it alone. 4/3 pi. Derivative of r cubed, 3r squared, dr dt. The 3 and the 4/3 will cancel. dv dt equals 4 pi r squared dr dt. Here's our first kind of simple related rates problem. This is kind of like a problem where we're going to get a number. We're going to find dy dt equals what? It's a number. All right? To find dy dt, I need some sort of expression with dy dt. I'm going to take the derivative of this with respect to t so that I see dy dt. I got dx dt equals 3y squared dy dt equals 0. Okay, this ends up just being like a simple problem. Dx dt is 2, y is negative 2, find dy dt. All right, so I got 4, 12, I got dy dt equals negative 1, 6. Just solve for dy dt. Okay, this is kind of the beginning of what we're going to be doing for the next 2 class periods. If x squared plus y squared equals 25, dx dt equals 5, find dy dt when y equals 3. Okay, so I need dy dt. Let's switch this because I don't want you to get confused. Let's say dy dt equals 5. Find dx dt. Again, I need some expression with dx dt, so I need to take the derivative with respect to t of x squared plus y squared. dy dt is 5. Okay, great. So 2, this is a 5. Y is 3. Okay, great. Trying to find dx dt, sweet. But I have a problem. What the heck is x? It didn't give me x. But that's okay. I can find x. I know x squared plus y squared x is equal 25. I will be able to find what x is when y is 3. Let's see. X squared equals 25 minus 9. That's 16. I'm told x is bigger than 0 and y is bigger than 0, so x is 4. This is an extra step that I have to do to find dx dt. I need to find that x is 4. I need to get 8. 2 times 3 times 5, that's 6 times 5 is 30. Subtract 30 divided by 8. I get negative 38, which is negative 15 fourths. Okay, same idea. Last one. T squared equals x squared plus y squared. Take the derivative with respect to t. I get 2z dz dt equals 2x dx dt plus 2y dy dt. I'm given a bunch of information. I want to find dz dt. Let's plug in the information. Okay, dz dt equals dx dt is 2. X is 5. dy dt is 3. Y is 12. I got one piece of missing information, z. Let's find z when x is 5 and y is 12. Z squared equals 5 squared plus 12 squared. Z squared equals 25 plus 144. Z squared equals 169. Z will equal 13. Now we can find dz dt. This is 20, 72, this is 26, this is 82, 82 over 26. What is that? 41 over 13. Okay, so this was quick. It was not paced at what is typically the correct pacing for a lesson like this, where you're doing some practice, but you guys will be able to practice doing your homework, and we can rewatch this video if you need to over the weekend. I should have a better paced video up on Monday, and I will have the homework video up on Monday. Sorry for being out today. Thank you, and I'll see you guys on Tuesday.